In the previous module, you learned an introduction to functions in programming. Much of what we talked about was very general and applies to many programming languages, and some specifics that we learned applied to Matlab. In this module, we'll pick up some more advanced topics in functions. The first topic we'll cover is function handles. How can references to functions be stored in variables? Well, you could certainly store the name of the function that you're trying to refer to in a character array, but you can also store a reference to a function in something called a function handle. Why would you bother? Sometimes it's necessary to pass a reference to a function into another function. Well, why would you ever need to do that? There are several algorithms, which of course have to be implemented as functions, that solve your problem by repeatedly calling a function that you supply. For example, there's a function in Matlab called f0, and it finds the zeros of a function. Which function? Well, you have to supply it the function that you would like it to compute the zeros of. There's functions in Matlab called trap, z, and quad, and they integrate a function. Which function? You have to pass in the function that you would like integrated. Integrating a differential equation is the purpose of the command ODE45. Which differential equation? Well, you have to pass in a function which describes the differential equation. Optimization algorithms, such as fmin bound and fmin search, minimize a function by choosing its input variable appropriately. Again, which function? The function that you'd like minimized. In all of these four examples, there's some sort of algorithm that's acting on a function. That's why we need to be able to store references to functions in variables. You should add this new object class, function handle, to the list of all the other classes you're familiar with: double, char, logical, and in fact, we'll learn about more classes as we continue through the course. The @ sign is the operator that is used to get the reference to the function from the function name. In this expression, the @ operator is applied to the sign function, returning the function handle to the sign function and assigning that to the variable shan. The class of shan is a function handle. Now, sign was a built-in function. Is that the only type of function we can get function handles for? The answer is no. We can also get a function handle to our vecop function, which we wrote. Again, the @ operator is applied to the function name, returning the handle to the function. Therefore, whos will confirm that both shan and vhan are variables in the workspace and that their class is function handle. Since the beginning of the course, we've known that we can call a function using its name and passing input arguments and asking for output arguments. Well, the same is true with the function handle. We can also call a function by its function handle. Here, I use the @ operator to obtain the function handle to the function myfunc, storing it in a variable fh, and then use fh to call the function. These two lines are equivalent to this line. Let's try this in Matlab. Assign to the variable shan the function handle to the sign function. Confirm that the class of shan is function handle. Let's try the same process on the mfile function vecop, which we wrote. And then use whos to confirm the behavior. Lastly, we should confirm that this really works. For instance, that vhan points to the function vecop. Let's create two vectors and compute the dot product and cross product by directly calling vecop. Let's also call it using the function handle. In actuality, the same exact code was executed, so these output arguments should agree exactly. Let's confirm that with the equal operator. The dot products are equal, and checking the cross product reveals that they're exactly equal as well, element by element. So function handles point to the exact code that they refer to. Let's summarize what we've learned and see one small restriction. we always use the @ operator with the name of the function to retrieve the function handle. That creates a variable of class function handle. Unfortunately, arrays of function handles are not allowed. This is really the one exception to the adage that in Matlab everything is an array. If you try to create an array of function handles, you'll get an error. Here we try to create a 2x1 array of a function handle to cosine and a function handle to sine, and this will produce an error. Try that out. That doesn't mean, though, that we can't store collections of function handles in one variable. In a few modules, we'll learn about cell arrays and struct arrays. In these, we'll be able to store collections of function handles. Let's conclude this unit with an example of how we can use a function handle. Remember the motivation for storing references to functions in variables. It was that several algorithms, or functions, solve your problem by repeatedly calling a function that you supply. For instance, f0 finds the zeros of a function. Here's a function that I have, and that's a graph of it. Suppose I'm interested in finding the zero very accurately, which you can see is located right about there. The function f0 can do that. I simply need to pass to f0 a handle to this function which I'd like it to compute the zero of. So we need to pass a function handle to f0. Let's create an mfile function representing this function. I'm calling it fz. On the bottom line you can see the formula representing the function. I've used element by element exponentiation and multiplication so that this function is already vectorized. If you give it a scalar x, it returns a scalar y, and if you give it a vector of x's, it returns a vector of the corresponding y values. Let's look at the syntax for f0. There are two input arguments. The first is the handle of the function that f0 is supposed to compute a zero of, and the second is an interval where it should look for that zero. Here I've used -2 to 2. The output argument is the zero itself. Let's produce the graph on the right along with the location of the zero, create a dense vector of x values, and plot the x values, the function values, the root, and the function at the root with a red circle, and that produces this graph.